We can wait for a moment for Gabriel. Okay, Gabriel started live streaming. Please go ahead.
Okay, thanks very much for having me. So I want to tell you about some recent work over the last few months with my student Jivan Chandra and also Scott Collier and Alex Maloney. But the story here goes back further to trying to understand the role of higher topologies in gravitational path integral. So let me start with a few words of introduction about that topic. So we learned a few years ago from Saad-Shanker and Stanford that two-dimensional gravity is holographically dual to random matrix theory. And this seems fundamentally different, at least at first glance. It seems fundamentally different from other stringing examples of ADS CFT, because random matrix theory, the boundary theory is not quantum mechanics. It's an average over quantum mechanical theories. And this is fundamentally different because, for example, observables in two copies of the boundary theory don't factorize. If in random matrix theory or in JT gravity, we calculate the product of two partition functions at two different temperatures, beta 1 and beta 2, then it has correlations. This has connected contributions that correlate the two copies. On the gravity side, those are realized by connected topologies. So this picture that I'm drawing here and all the pictures that I'm going to have in this talk are Euclidean wormholes. This is a space-time Euclidean wormhole. The two boundary circles here are the thermal circle in quantum mechanics number 1, thermal circle in quantum mechanics number 2, and there's a Euclidean space-time that's joining them. Now, in this case, this is an off-shell path integral. It's not a solution of JT gravity, but the kinds of things that I'm going to talk about are mostly solutions, actually. So that's two dimensions, but there are many reasons to suspect that averaging or some kind of ensemble or coarse graining of some kind plays a role in higher dimensional gravity as well. For example, there are space-time wormhole saddles with no known instabilities. If anything, the problem is more striking and more clear in higher dimensions where we actually have solutions like this that connect the two sides. And we think, or it seems that they're under semi-classical control, so we need to understand what they mean. Now, I am not saying that UV complete quantum gravity is an ensemble average, just that these connected contributions seem to have some important role to play in understanding the low energy theory, and we should understand what role that is and how to interpret them. I think that the common lore, say 10 years ago, was that you should just throw away these contributions. They're obviously nonsense. They can't possibly contribute. Let's just not talk about them. But one thing we've learned from two dimensions is that is too quick. We need to take these seriously and understand what they're telling us about quantum gravity and the gravitational path integral. Okay, so this raises the question, what is the role of higher topologies and multi-boundary geometries in more than two dimensions in quantum gravity? And in this talk, I'll describe a class of on-shell Euclidean wormholes in any number of dimensions, higher D, and I'll discuss their CFT duals. I'll actually talk about various types of wormholes, but they all sort of fit into the same class. And I'll talk about two different CFT interpretations. There's two different ways of thinking about the contribution of wormholes. They're not mutually exclusive. They're both consistent. They can both be true. The first is as coming from averaging. We can think of these wormholes as coming from averaging over an ensemble of CFTs. That is vaguely true in all dimensions. In two-dimensional CFT, it's something that we can make very explicit and define exactly what we mean by averaging over CFTs and do some detailed checks. In higher dimensions, it's just a vague proposal that it should have something to do with averaging, but we don't know how to average over CFTs in more than two dimensions. The second interpretation is in terms of coarse graining. And I'm making a distinction in terminology here. So averaging means averaging over different theories, whereas coarse graining is something that's done in a fixed theory. Okay, so by coarse graining, I mean in a fixed theory, defining some observables that are insensitive to the UV. So that discard or are insensitive to some UV information in that fixed theory. So these are two different ways of thinking about it, and we can phrase many of these results in either language. So in outline, I'll start by discussing the wormhole solutions in d dimensions. Then I'll talk about the coarse graining interpretation that holds very generally in any number of dimensions. And then I'll narrow in on 2 dimensions where we can go further. The kinds of wormholes that we can construct in 2 dimensions there's a much wider set of wormholes that can be constructed in 3D gravity, simply because the gravitational equations are easier to solve and analyze. So we can go further in that case, and there I'll talk about how we explicitly define an average over 2-dimensional CFTs. So let me start with the wormhole solutions in d dimensions. So this picture is something I want to dwell on for a minute. This is probably the most important thing I'll put up here. So let me explain what this picture is. So this is the kind of wormhole that we're going to construct and discuss. This is a on-shell Euclidean solution of ADS gravity in any number of dimensions. It's not a vacuum solution. It's supported by supported by matter. So in this case, what I'm drawing here is a solution with 6 asymptotic boundaries. Those boundaries are not connected to each other. They're completely disconnected boundary components, even in Euclidean signature. So this is a space-time wormhole, not just a Einstein-Rosen type wormhole. The matter here is spherically symmetric. So I'm just drawing 2 of the directions, but there's an additional d-1 sphere at each point on this diagram, with the exception of the edges, which is like where that sphere degenerates. That's a pole of that sphere. So there's a spherically symmetric matter source that supports a solution with k asymptotic Euclidean boundaries. The reason I'm talking about spherically symmetric matter is I think not a theoretical restriction. It's just a matter of being able to solve the Einstein equations. When we construct these wormholes in d dimensions, well, it's hard to solve the Einstein equations without some symmetries. So we restrict to the spherically symmetric case. But I'll come back and talk about solutions without spherical symmetry when we focus on 3D gravity later. There are previous wormholes in d dimensions. This is not like those. So as far as I know, the previously known wormholes in d dimensions involved sources everywhere in the boundary. So that involves a true deformation of the boundary theory, where you actually, for example, the boundary conditions don't correspond to n = 4 super Yang-Mills. They correspond to some deformation of that theory. Whereas the wormholes that I'm going to be talking about just have the ordinary boundary conditions and correspond, therefore, to some calculation in the usual CFTs that we talk about in ADS CFT. The wormholes I am talking about are more like some examples that have been discussed in lower dimensions, like this 2D West Coast model, which is a model of JT gravity plus matter, or in this 3D model that I'll discuss later. So I'm going to describe how these spherically symmetric wormholes are constructed. It's actually pretty straightforward. The bulk theory can be just about anything, actually. These solutions exist generically for various types of matter. But to be concrete, I'll focus on Einstein gravity plus a pressureless perfect fluid. So that is Einstein gravity plus dust. The strategy that will follow to make a wormhole is to cut and glue k copies of a collapsing black hole. So we're going to start with a black hole, and then we're going to chop it up and use it to construct So the black hole has just one boundary, but we're going to use that as a starting point for the K boundary solution. So our starting point is a black hole pure state. That is a black hole that's formed by a gravitational collapse. In this example, we're going to use a thin shell gravitational collapse solution. So this solution is something that you can write down explicitly in d dimensions. And here's how it goes. You start with a eternal black hole. That's the picture on the right. What I've drawn here is the eternal black hole in Euclidean signature. So this is the thermal circle and the radial direction. As always, there's an additional d-1 sphere at each point. So we start from the eternal black hole. Then we put a thin shell of matter behind the horizon of that black hole. So I say behind the horizon because if I put this horizontal line here, that's the t=0 slice. So by putting this thin shell over on the left side of the diagram, we're putting a shell behind the black hole horizon. And we're gluing across that shell to empty vacuum global ADS on the other side. Okay, so there's a region of global ADS inside the shell. Then there's a shell, and there's eternal black hole on the outside. So the equations of motion for the shell are given by the Israel junction conditions. So what you need to do is you need to solve those junction conditions given some surface stress energy at the shell. This gives you an equation of motion for the shell, which can't be solved in closed form, but it's just a simple integral in order to be able to plot solutions like this and to construct them by solving, but just by doing that numerical integration. So that's the solutions we're talking about. To start with, this is a pure state. So although we started with the eternal black hole, the solution that we have at the end of the day does not have a thermal circle. If you follow this dark black line, that's the boundary. If you follow that boundary through the shell, then you land over here. So that there is no thermal circle. This is a pure state where we can think of, if you think of having the vacuum state down here, then you insert an operator that creates the shell. Then you evolve for a while, and then you insert the conjugate of that operator. So what the path integral is calculating in this scenario is the norm of the state created by the shell operator, which I've called V. So this path integral calculates V dagger V. It's not a thermal trace. Now we can go to the wormholes. So as I said, to make a wormhole, we're going to cut and glue K copies of this pure state black hole. The first step is to cut it up. So by cut it up, I mean that we put we just take a piece of it, a wedge of this. I'm not going to keep drawing the vacuum region. I'll just draw the black hole region. So this is the black hole region of one of these collapsing black holes. And we're going to cut out a wedge of it with an angle 2 pi over K. And the reason we want to do that is that once we've done that, we can now glue together K copies of that wedge just by repeating it around the circle. And we now have a wormhole because this is now smooth. The point at the center is smooth because of the way we've chosen that deficit angle. But the way we've glued them together, you can see that now we're left with 3 copies in this case of the asymptotic boundary. So the example I've done here is with K equals 3. So by gluing together 3 copies of this collapsing black hole, we now have a 3-boundary wormhole. Again, this is a space-time diagram. So it's really 3 distinct Euclidean boundaries that are not connected to each other. A few comments about this construction. So that's the spherically symmetric construction. It's that easy. We just have to take this pure state black hole, chop it up, and glue it back together. A few comments. First of all, it's clear from this construction that there will be a K max. Given any black hole, if I try to make K too large, this angle will get smaller. So this wedge will get smaller, and eventually I'll hit the shell itself, and this construction that I've described will break down. So any given black hole has a K max, and this construction works only for the number of boundaries K up to K max. A second comment is that we want the boundary conditions to correspond to K copies of our original calculation, V dagger V to the K. So we need to fix tau 0, which was the original place where our operator V was inserted in the Euclidean time. So that can be done just by setting some boundary condition, and ends up giving it tells you that you need to use a different temperature. You need to start with it if you want to replicate the black hole at temperature beta. The replicas actually are obtained by chopping up a black hole at a different temperature in order to satisfy that boundary condition. There's a question. Go ahead.
Sorry, I was muted. So the Kmax depends on the mass of the black hole concerned?
Let's see. Kmax will depend on it will depend on where this point is. So it depends on where the shell lands. And that depends not just on the black hole, but on the details of what the black hole is made of. So it depends not just on the mass of the black hole, but on the details of this microstate.
I see. So, I mean, but somehow we have to get an integer out of all that, right?
Actually, Kmax is not an integer.
Oh, I see. Okay.
Yeah, oddly, Kmax is not an integer.
Okay.
But actually, these wormholes that I've described make sense for non-integer K. Because if you just think about this picture, don't think about the second one where I've glued them together. Just think about the one on the left.
Mm-hmm.
This picture makes perfect sense for non-integer K, and you can think of this as a quotient of the wormhole mod ZK. So this picture makes sense for non-integer K, and in fact, the match to CFT that we'll find eventually also works for non-integer K. It's not required to be an integer.
Okay, thank you.
Now, a limitation of this is that we only get cyclically symmetric wormholes by this construction, but then you can perturb them in order to at least order by order. In principle, you could calculate the non-symmetric cases. So I've described the case of a thin shell black hole, but it's actually quite generic. Another case that we've worked out in detail, and so is the end of the world brain black hole. So this is a black hole microstate that's been studied quite a bit in the literature. The picture looks very similar. The only difference, well, the main difference with an end of the world brain black hole is that this red line here is not a thin shell with some vacuum behind it. It's just an end of the world brain where space-time terminates. The equation of motion for the end of the world brain is different than the equation of motion for the thin shell. And it leads to another key difference, which is that these end of the world brain black holes do admit wormholes, but only with K less than 2 boundaries. Okay. K max in that case is always less than 2. So you can't actually form true multi-boundary solutions in that case. You can only form these fractional wormholes where K is somewhere between 1 and 2. Go ahead, Nikolai.
Hi, I have 2 questions. They might or might not be related. I'm not sure. One is about the operator V. It should be a heavy operator of some sort?
That's right.
Yeah, okay. And then what happens on the edges of these black regions? Should I think of this as a CFT on an interval with some specific boundary conditions, or?
In this case, no. So what's happened? So if we were doing the end of the world brain black hole, then the answer would be yes.
Yes.
But what's happened here is that each of those things is one of these gluings. I just didn't draw the glued piece.
Oh, I see. I see. So I should be thinking of each of the edges as actually having a like a minus infinity or plus
Yes,
infinity.
there's like another boundary segment coming out this way that goes all the way to infinity. And that's like the preparation of the state. And then here we insert the operator and then we evolve it.
Okay. And the dimension of V should scale with C or?
Well, V is not a local operator. It's a spherically symmetric operator.
Oh, you've integrated over a sphere. I see.
Well, if you'd have to, one way you could do it is by integrating over a sphere and exponentiating.
Okay.
Or you could take a product of operator insertions all around a sphere.
Okay.
Think of it that way.
Okay.
But it's a heavy operator in the sense that if you calculate the energy in that state, it will be order C.
Okay.
Because it's making it's making a black hole. So.
Thank you.
Yeah, I described it as putting a shell in a black hole, but really physically what's happening here is this operator is back reacting to make the black hole. So it really is just getting the black hole from acting on with this operator on vacuum. Okay, so what is the CFT interpretation? I've described some solutions. These are solutions of Einstein gravity plus very generic matter. I think that it would be straightforward to embed this in top-down examples with one caveat, which is that we'd have to check whether they're stable. I don't know whether they're stable, whether these are stable solutions, but that question aside, you can certainly embed these into top-down examples. And what we're going to do is just plow forward and look for a CFT interpretation. Now, naively, these solutions, just by the ordinary ADS CFT dictionary, would contribute to the calculation of V dagger V to the kth power. That is just k copies of this overlap. By what I mean by naively is that if we just follow the usual rules of ADS CFT, that would tell us that to calculate V dagger V to the k, we should look at some boundary conditions that have a bunch of copies of the ADS boundary with the insertion of V and V dagger. And this is the boundary conditions that these wormholes satisfy. So naively they contribute. However, this of course doesn't seem to make sense because this observable is just a core, it should have no connected contributions, just like these products of partition functions that we talked about in the introduction. This is just a number raised to the kth power. From the point of view of the boundary CFT, obviously there are no correlations. This is, of course, the factorization puzzle in this context. So we need to be more careful about interpreting them. And now I'm going to describe the interpretation in terms of coarse graining. As I said, there are different ways to interpret this. You can interpret it as an ensemble average. You can interpret it as perhaps it's the typical size of certain contributions in a given theory. I'm going to describe this coarse graining interpretation. The short summary is that these wormholes prepare a coarse-grained state in the dual CFT associated to that black hole, but it will be a coarse-grained version of that black hole. Furthermore, these wormholes can be used to define a natural coarse-grained entropy in a pure state. So to understand intuitively what's going on here, so I just want to explain why these wormholes should have anything to do with the words coarse graining. What does this have to do with wormholes? So to explain this, let's consider the Lorentzian geometry of the thin shell black hole that we started with. So this is the thin shell black hole. I didn't draw the vacuum region, but this is the one we were starting with, the black hole pure state. If we take this geometry and chop it at time 0 in Euclidean, then we can evolve that into Lorentzian time. And the Lorentzian spacetime looks like something on the right. So it's time symmetric, since we prepared it from this time symmetric Euclidean spacetime. So it's time symmetric. And at time 0, there's a shell of matter behind the horizon. The horizon here is so there's a horizon which already exists at time 0, and that horizon we can see by looking at the spatial geometry of the slice, this t = 0 slice. So it looks like this. There's a horizon, which is an apparent horizon, which is a minimal area surface on that spatial horizon. Then there's a matter shell behind that horizon. Good. So this is the geometry of this black hole at the initial time. Now, there's an apparent horizon here, which suggests that there's some kind of entropy associated to this state. However, this cannot be the von Neumann entropy, because this is a pure state. The von Neumann entropy is exactly 0. And if we were to apply the Ru-Takanagi formula here, well, we might think that there's a Ru-Takanagi formula because there's a minimal area surface. But if we apply the Ru-Takanagi formula here, we just get 0, because this surface here is homotopic to nothing. It's trivial. We can just take this surface gamma and slide it off the end of this space smoothly. So the actual Ru-Takanagi surface here is the nothing surface, and it correctly calculates the von Neumann entropy, which is 0. So there isn't a von Neumann entropy, but you might think that there's some other kind of entropy associated to this horizon, some kind of coarse-grained entropy. And so our black holes, the wormholes rather, the wormholes that I've described, one way of saying how you get these wormholes is that we've constructed replica geometries that glue this together that glue together branched around the minimal surface. So we've glued together many copies of this black hole and then allowed it to back react to produce a smooth solution. That's really how we constructed those wormholes. And what all this suggests is that our wormholes are related to the coarse-grained entropy. And therefore, it should be possible to use these wormholes to deduce the coarse-grained state in the dual CFT. So that there should be some kind of coarse graining procedure that you can apply to a pure state black hole to get a mixed state, and that these wormholes are telling us about that coarse graining procedure. So that's the picture here. This idea that apparent horizons like this one are associated to coarse-grained entropy is one that's been studied in detail by Engelhard and Wall, and they have a proposal for how to coarse grain a bulk geometry. What I'm going to describe is a similar motivation, but it's a bit different because I want to give a CFT formula. Our goal here is to derive an explicit CFT formula for the coarse graining, for the coarse grained state. Their picture is more on the bulk side. We're trying to get a CFT formula. Ultimately, I think that they should agree, although we don't understand precisely how to get from one to the other. Okay, so the proposal for the CFT interpretation of these wormholes, that background is the following. Expand the thin shell pure state black hole in energy eigenstates. So we take that state that we get by acting with the shell operator V and just expand it in eigenstates in your CFT. Then we claim that the wormhole computes the norm of a state psi k. So that is the e to the minus gravitational action of this wormhole is the overlap of psi k with itself, where psi k is a particular entangled state in k copies of the CFT that you get just by taking that. You just take your expansion in energy eigenstates and take a tensor product to the k. This is similar to a GHZ state that's discussed in quantum information and qubits, where you just have for example, like 0, 0, 0 plus 1, 1, 1 is the classic GHZ state. So the claim is that this wormhole is calculating the norm of a GHZ state. That's the basic proposal. Now there are earlier it's well known actually in the study of holographic entanglement that you cannot prepare GHZ states holographically, but there's a loophole in that, which is that you can't prepare them on smooth slices. And these GHZ states that I'm talking about are associated to non-smooth, sort of jaggedy slices of the wormhole. So there's no contradiction. So what does this have to do with coarse graining? Well, there's another way of saying what I've just told you, which is the following. We start with a pure state. Now I'm writing just the density matrix for our pure state thin shell black hole, just by taking our pure state and expanding again in Ng eigenstates. Now this density matrix is pure, so it obviously has von Neumann entropy equal to 0. Now we define a coarse-grained state, a coarse-grained density matrix, by taking the diagonal projection in the energy eigenbasis. So we just keep the diagonal elements of this density matrix. This gives us a mixed state. So this is some procedure you can do to any density matrix. And we started with a pure state black hole. We took the diagonal projection and now have a mixed state. And the formula on the previous slide can be recast as a statement that the wormhole calculates the replica partition functions for the coarse-grained state. So let me say that again. So we started with the pure state. We define this map to coarse-grain the state. And then the claim is that the gravity side, the wormhole on the gravity side, corresponds to the replica's trace rho bar to the k, not for the original state of the black hole, which has trivial replicas, but for the coarse-grained state. So that's the basic relationship here. This equation is derived by explicit calculation of both sides. So this is just something that we guess and confirm by calculation. The calculation that's done here is we first use the pure state black hole to determine the expansion coefficients an squared. Not exactly, because we're not doing string theory here, we're doing low energy gravity. So we can determine them up to some fluctuations in the UV, some fluctuating part in the UV that's undetermined. Then once we've found those expansion coefficients, we then match the gravitational action to CFT as a function of K. So that gives a very non-trivial check of this formula. So the punchline is that the wormholes on the gravity side tell us how to coarse-grain the density matrix of a thin shell black hole. What they've told us is that the coarse-grained state is the diagonal projection in the energy basis. I should note that there are ambiguities in this because when you calculate trace rho bar to the k, that's invariant under unitaries. So this is not a unique answer. If all you do is check the partition function, we can only say that this is a state that has the right entanglement spectrum. And there could be, if we want it to be the full-blown correct coarse-grained state, we'd have to also check other observables. Now that we've prepared the coarse-grained state, we can talk about the coarse-grained entropy. The entropy of the coarse-grained state can be obtained by the replica method. We've already calculated, yes, there's a question?
Yeah, I was wondering if you could get some intuition about what kind of coarse graining is this? I mean, I can understand, in terms of the density matrix, what you have done, but it's not like coarse graining looking at low energy states or anything like that, right?
Yeah. Well, I'll have let me come to it in one. Let me come to it in 1 second.
Okay.
I don't have great intuition for what this means, but I'll have a little bit to say about it. And
Okay.
yeah. Okay. So if we look at the entropy, the entropy, well, if you can calculate trace rho bar to the k, then the standard replica method tells you can also calculate the entropy of this coarse-grained state, because that's just the replica partition function for k near 1. We just take this derivative near k equals 1 that gives us the von Neumann entropy, not of the original state, that would be 0, but of the coarse-grained state. Since our coarse graining was a diagonal projection, we now have a formula, a microscopic formula for the coarse-grained entropy of this thin shell state. Is just the diagonal part of rho log rho. Now, coming back to Sumit's question, what is this thing? Well, it actually, this is something that's been studied before and was introduced by condensed matter theorists. It's a quantity called the diagonal entropy. And the reason they introduced it was they were looking for, so they were studying quantum systems out of equilibrium. And they were looking for some good definition of entropy in pure states for these chaotic quantum systems. And they were studying this in the context of the eigenstate thermalization hypothesis. So the reason they introduced this quantity is basically because it acts like an entropy in theories that satisfy ETH, eigenstate thermalization. In these theories, they found that it satisfies a thermodynamic first law and a second law under stochastic evolution. So that's the best I have for intuition for this. It's something that acts like an entropy that makes sense in pure states and acts like an entropy in chaotic theories.
So it is tied very much to the energy basis, but it's not quite. I see. Okay, I got it.
That's right. That's right. And I think that's for the same reason that ETH is tied to the energy.
I understand. Yeah.
It really is special, and it's
context,
only true in that basis. Yeah.
Good.
So to sort of summarize what I've just described, you could say that these wormholes we constructed in the first part of the talk are the replica wormholes for diagonal entropy. I could have given the whole talk in the other order, where I said that, okay, there's this thing called diagonal entropy that condensed matter theorists are interested in. How do we calculate it holographically? And for thin shell black holes, we would have landed on this set of wormholes to calculate the diagonal entropy. There's the bulk interpretation of this entropy. So closing the circle here, the bulk interpretation of this entropy is that it is the area of the apparent horizon. We're talking about these pure state black holes, and I started this discussion by saying that they have some kind of horizon that has some kind of coarse-grained entropy. What could it be? Well, now we know, since these wormholes are associated to replicas around that surface, the results of Lefkowitz and Maldacena on the gravitational replica trick tell us that the diagonal entropy is calculating the area of this apparent horizon. So this is our microscopic CFT formula for the area of the apparent horizon of a thin shell black hole. For more general black holes, the coarse graining map is not just a diagonal projection. I've discussed the simplest case, which is these thin shell black holes that are locally eternal black holes. But as soon as you start perturbing them, adding more matter, looking at more complicated black holes that are not locally the eternal black hole, you can still try to go through this procedure where you use wormholes to determine the coarse graining map. But it's something much more complicated. In general, it seems to be very difficult to find explicitly. We have done it for perturbations of the thin shell black hole. Say you just add one particle outside the horizon, then we know how to calculate the coarse graining. We know how to follow this whole procedure through. In that case, you construct the wormholes, you find a coarse graining map. It's not just a diagonal projection. It's something more complicated. It's a more complicated coarse graining, which is something inherent to holographic theories, which agrees with the diagonal projection in simple cases like the thin shell black hole. So that's all I have to say about the general case and the interpretation in terms of coarse graining. In the last part of the talk, I want to talk about the other interpretation in CFT, which is in terms of an ensemble average. Maybe before we go to the last part, I'll pause here and see if there are questions about what I've talked about so far. Okay, so let's proceed. It's all going to tie together, but it is sort of a different topic. So far I've discussed wormholes with spherical symmetry in d dimensions. And in 3D gravity and 2D CFT, both on the gravity side and on the CFT side, we can go further. Okay, so there are lots of wormholes that we can construct explicitly and study in detail in 3D gravity. I've drawn a picture of some of them. There are two boundary wormholes, which you can find solutions. Let's start with this one here. So this is a two boundary wormhole with higher genus boundaries that was discussed by Maldesain and Maus in a well-known paper in 2004. There's a whole class of wormholes like this where you take a hyperbolic manifold, a hyperbolic two manifold that is, and the wormhole has the topology of that times an interval. So you can do that with higher genus. You can do that with defects. So this example here, which I'm going to talk about in some detail, is an on-shell solution of 3D gravity with 4 conical defects or massive particles that have a world line stretching from one boundary to the other. So these are all Euclidean. These are all on-shell Euclidean solutions of 3D gravity. There are more complicated cases where you take a bunch of particles propagating amongst many boundaries. You can also get these sort of handle type geometries where you have just one boundary, but there's some non-trivial topology in the bulk. So there's all sorts of things that one can do. Now, I strongly suspect that similar wormholes exist in higher dimensions. There's no reason that they wouldn't, but it's just hard to solve the Einstein equations without some extra symmetries. So these are the non-spherically symmetric version of the wormholes that I discussed in the first part. And one of the big advantages of working with these non-spherically symmetric ones, like this one here, is that now we're talking about correlation functions of local operators. In the first part, I was talking about correlation functions v dagger v to the k, and v was a very complicated spherically symmetric black hole making operator. Okay, so that was something that was very useful to do in the bulk because of the spherical symmetry, but is a very inconvenient quantity to study in CFT. In CFT, we usually talk about we usually talk about correlation functions of local operators, because that's what's directly related to the usual CFT data. So the story I want to tell now is how we can go further by both in the bulk by constructing these more complicated wormholes, local sources, and also in the CFT, because now we can relate these to the standard data of a CFT. And this led us to the conjecture that the CFT dual of these wormholes is an ensemble average over approximate solutions of the bootstrap equations of a 2D CFT. This is a precise statement, so I'm going to explain what's meant by this average, what it means to do this CFT average. There's two calculations here which are equal to each other. There's a gravity calculation of the action of these complicated wormholes. In many cases, not every possible wormhole, but at least in all the cases that are on this slide. So that's a gravity calculation, and there's a CFT calculation that I'm going to tell you about where we we define this average over solutions of the bootstrap equations. Okay. Now, I've told this in reverse order, so we actually did the 3D case in an earlier paper that was in collaboration with Jivan, Scott, and Alex, and then Jivan and I did the spherically symmetric case later, but I'm just presenting it in the opposite order. Now, these wormholes in 3 dimensions also have a coarse graining interpretation, and that's interesting. It's just along the same lines of what I described in the first part of the talk, where you coarse grain a state in a fixed CFT. That can be done as well in 3 dimensions, but here I'm going to describe the averaging, the ensemble averaging interpretation. I'm going to focus on this particular example. There are lots of different wormholes we could talk about, but this one illustrates all the main points. So let me explain what this wormhole is again. This is a solution of 3D gravity coupled to massive particles. So there are 2 asymptotic boundaries, which are 2 spheres. So there's a 2-sphere asymptotic boundary here. There's an asymptotic boundary 2-sphere over here. And each sphere has 4 local operator insertions, which in the bulk become these massive particles on space-like trajectories connecting the 2 boundaries. Since there are 4 operator insertions here, there's a conformal cross ratio on each boundary. So there's a conformal cross ratio of those 4 points that I'll call X on the left, and another one, independent cross ratio X prime over on the right. If the moduli at the 2 ends, that is these cross ratios, at the 2 ends are not too different in a way that's been studied by mathematicians long ago, then this is related to what's called an almost Fuchsian group. So the solutions of 3D gravity are related to quotients of H3 by subgroups of SL2C. And in this case, it's related to quotients by an almost Fuchsian group, which is a technical term introduced by Uhlenbeck. So if these are not too different, then the metric on this wormhole can be written down very, very explicitly. Well, almost explicitly. Here it is. So rho is the direction, is the radial direction. Minus infinity is on the left, plus infinity is on the right. And then there's some extra stuff in here. The things that are showing up are a Liouville field. So there's a Liouville field phi. It's important, in order to get wormholes like this, it's important that the cross-sectional slice of the wormhole is a hyperbolic geometry. So that Liouville field is related to putting the hyperbolic metric on each cross-sectional slice. And then finally, there's a quadratic differential T bar of Z bar. And that's just another thing you can specify freely in this wormhole. The quadratic differential ends up giving you the difference between the moduli on the left and the moduli on the right. Not in a simple direct way, but in a very indirect way. The quadratic differential parametrizes how different the moduli are on the 2 ends. You can think of that as like a momentum, an initial momentum kick that's given to some of these particles that sets them moving so that they land on the other boundary at a different cross ratio. So we calculated the gravitational action of this wormhole and a class of related wormholes. This is just a gravity calculation. And we found the following surprisingly simple result. Okay, so the gravitational action of this wormhole, the on-shell action, e to the minus s of that, is a correlation function in Liouville CFT. This approximately means that this is true in the limit of large central charge and the semi-classical limit. Okay, so this on-shell action is a product of 2 Liouville CFT correlation functions. Each of these is a Liouville 4-point function. a funny thing here is the way the cross ratios show up. Okay, we started with a gravity calculation in Euclidean signature with a cross ratio x conjugate x bar on the left, x prime on the right. But the Liouville correlation functions are in Lorentzian signature, because the arguments here of the Liouville correlation function are not complex conjugates of each other. That means this is a Liouville CFT in Lorentzian. The z and z bar have been decoupled. So this Liouville you can think of as encoding the left movers on the two boundaries, and this other Liouville you can think of as related to the right movers on the two boundaries. It's not one Liouville for each boundary; they get mixed and matched. So this is the result of this calculation. And now I want to turn to the dual CFT and understand what this has to do with averaging over CFTs. The dual CFT here is not the Liouville CFT. That showed up as sort of an accident in this gravity calculation, but we're going to see how it's related to the dual CFT now. Now, naively, this wormhole contributes to the product of CFT 4-point functions. By naively, I mean if you follow the usual rules of ADS CFT, then calculating a product of 4-point functions like this means that you should put boundary conditions where you have a sphere with 4 operators and another sphere with 4 operators, and then you should consider gravity, the gravitational path integral that has those boundary conditions. And that's the boundary conditions that we have on this wormhole. So this is a product of 4-point functions of local operators in the dual CFT. The two 4-point functions can have different cross ratios. This is naively what it's supposed to calculate, but in a single CFT, this cannot have connected contributions. It makes no sense. This is a factorization puzzle again. So we define an average over large central charge CFTs as follows. And the reason we're talking about large central charge CFTs is that what we're trying to do is define an average over holographic CFTs, or over CFTs that are at least roughly within the plausible class of theories that could be holographic, and therefore they have to be CFTs with a large central charge. And we're going to define this average as follows. First, expand the CFT observables in conformal blocks. Okay, so I've just taken the product of 4-point functions and expanded each 4-point function in Virasoro conformal blocks, so we get a double sum over primaries P and Q in 2 copies of the CFT. These are OPE coefficients, and these are Virasoro conformal blocks. So far, that's just true in any theory. But now what I want to do is define an average. So to define an average over CFTs, what we need to do is specify the statistics of the OPE coefficients and spectrum appearing in this spectral decomposition of the 4-point function. So to define an average, I need to tell you the statistics that calculates this CCCC on the right. We're just going to take the simplest guess that's consistent with 3D gravity, and that's going to turn out to work. We assume the spectrum follows the Carty formula. That's known to be true in any theory that's dual to 3D gravity. So we assume the spectrum follows the Carty formula, and we treat the OPE coefficients as Gaussian random variables with the following statistics. They have 0 mean. The OPE coefficients have mean 0, and they have variance given by the following formula. So the variance is a function C0. C0 is a known function that's been explored earlier from the conformal bootstrap. Basically, once you declare that the OPE coefficients are Gaussian random variables, you can use the bootstrap to determine what has to go there in the variance by asking that it be consistent with crossing symmetry. So C0 is a known universal function that's been studied earlier. We're just gonna, so this is like the minimal consistent thing that could plausibly have something to do with gravity. It satisfies the bootstrap constraints. It has the spectrum of black holes of 3D gravity. It has large central charge. So at least we've put in the sort of very rough features of what you'd expect a holographic CFT to satisfy. And now we're just going to do the average. That is, we just plug in this statistics into that conformal block expansion, reorganize things a bit, and you get a formula like this. It's an integral of the Carty density of states times this universal OPE function times a bunch of Virasoro blocks. Well, miraculously, this reorganizes into a product of Liouville correlators. This universal function C0 is related to the DOZZ structure constants of Liouville CFT, that is, to the 3-point functions of a Liouville CFT. So there's an explicit formula for this C0. There's also just an explicit formula for the 3-point functions in Liouville CFT. And once you put in all these factors and the Carty density of states and everything, you find somewhat miraculously that this average is the product of Liouville correlation functions. And it's a product where, again, these cross ratios got switched around. So we're calculating an average, we're calculating a CFT average in Euclidean, and the answer is a Liouville correlator in Lorentzian. The upshot then is that the wormhole action matches the CFT average. Because when we calculated the on-shell action of the wormhole, we found a Liouville correlation function. Now we've calculated a CFT average just by sort of doing the simplest thing that seemed consistent with basic principles and gotten the same answer. So on the left-hand side is the gravity calculation. On the right-hand side is this average over large C CFTs in 2 dimensions. I've described this for a particular wormhole, which is a 4-point function squared, but we've verified this formula for all of the 2-boundary wormholes that I showed a couple slides back, with any genus, any number of operator insertions, and we've also checked the one-loop corrections to that calculation. Those also agree. We've also checked it for some special highly symmetric K-boundary wormholes, more than 2 boundaries, that is. So I'll just wrap up with some conclusions. Euclidean wormholes have an important role to play in low energy gravity. In this talk, I've described some explicit solutions where we have on-shell semi-classical solutions of gravity coupled to matter. In any number of dimensions, we constructed wormholes that look like this with spherical symmetry. In 3 dimensions, we were able to go further because it's easier to solve the Einstein equations, and found a bunch of multi-boundary wormholes that have point-like defects, higher genus, etc. So these have some important role to play in gravity, but they must be interpreted carefully because of the factorization puzzle. I've discussed 2 consistent interpretations that don't have an issue with factorization, importantly. In any dimension, we showed that these wormholes prepare coarse-grained states in a fixed CFT. We started with a pure state and described how the wormhole assigns a coarse-grained state, rho bar, to that pure state. That coarse-grained state has an entropy, and we gave that interpretation in terms of the area of the apparent horizon. In 3D gravity, we've also reproduced wormholes by averaging over OPE coefficients in large C CFTs. These are 2 different ways of stating what's essentially the same fact. You can either phrase this as coarse graining, or you can phrase it as an average. In both cases, it's an explanation for what low energy gravity is telling you about the dual theory or class of theories. And